Section 6.3. The dependence of the Gibbs and Helmholtz energies on P, V, and T. First, Helmholtz energy. dA equals negative S dt minus P dV. When the volume is constant, dA over dt is negative S over here, and entropy is always greater than 0. Therefore, when temperature goes up, the Helmholtz energy decreases. Similarly, when temperature is constant, dA over dV is negative P. Pressure is always positive. Therefore, when volume increases, A decreases. Similarly, we can analyze G. dG equals negative S dt plus V dP. And therefore, dG over dt is negative entropy. That's negative when pressure is constant. When temperature is constant, this part is 0, then dG over dP is volume. Volume is always positive. Therefore, when pressure increases, G decreases. Now we can analyze how G depends on pressure quantitatively. Delta G, this is the difference between the Gibbs energy at pressure P versus the Gibbs energy at pressure 1 bar. So delta G is G of P minus G of 1 bar. This means standard state. And then we simply just need to integrate this delta G over delta P. And this part is simply volume, given this equation here. And then we just need to integrate volume, dP, from P naught to the target pressure. If we have an ideal gas, it's very easy. Volume is nRT over P, so we just need to integrate this. The result is nRT times the logarithm of P over P naught. This P prime is a dummy variable. This P prime is from P naught to P. And then we can tell that the molar Gibbs energy of a gas with a pressure P versus the molar Gibbs energy of that gas in a standard state has a difference. The difference is simply RT times ln P over P naught. For a liquid or solid, it's easier because the volume of a liquid or solid is approximately constant no matter how you change the pressure. And therefore, if this V is constant, we can take this V out of the integral. And therefore, G of P minus G naught is simply the volume times the pressure difference. What about real gases? Well, for real gases, G of P minus G in the standard state is approximately this nRT times ln P over P naught. Molar Gibbs energy is an intensive property. Again, this G is extensive, N is extensive, but extensive divided by extensive is intensive. And this is molar Gibbs energy in the standard state. G is H minus Ts, therefore Gm is Hm minus Tsm. M stands for molar. How does the Gibbs free energy depend on temperature when the pressure is constant? Well, again, we have this equation here. This is because dG equals negative S dt plus VdP. When pressure is constant, VdP is 0, then dG is equal to negative S dt. So we have this equation. And then from this equation, we can prove this equation. The reason we do this is because typically it's difficult to measure entropy directly. It's a lot easier to measure enthalpy. So let's prove this. The left-hand side is here. At constant pressure, we'll just, for convenience, replace delta with D. And then we're going to just use the product rule. So we view this as G multiplied by T to the power of negative 1. And then we have T to the power of negative 1 here, times dG plus G times negative 1 over T squared times dt. And then what we need to do is we'll simply have this dG over dt at constant pressure. That's just entropy, right? So we'll just use entropy here. We got this entropy here. And also we have a second term. This term, if you cancel dt with this dt, you get this second term here. Now if you look at these two terms, we can combine these two terms because they have a common factor. the common factor is negative 1 over T squared. And then we have G plus Ts. What's G plus Ts? That's the definition of H. All right? And also, we can prove this. If you look at this G over T with respect to 1 over T. If you do this, you compare this derivative with this derivative. The difference is the bottom. But also, we can have this derivation. The exact differential of 1 over T is negative dt over T squared. I'll let you prove this. It's very simple. This is because the first derivative of 1 over T is negative 1 over T squared. So we can replace this guy with negative dt over T squared. And this negative 1 over T squared is on the bottom, so we flip that up. We get this negative T squared here. And then we know what this is. This is simply here. Okay, so what we do, or this one, what we need to do is we cancel negative T squared and negative T squared on the bottom. The result is H. So it's kind of interesting. If you make a plot with 1 over T as the vertical horizontal axis, G over T as the vertical axis, and then you look at the slope. The slope is actually the enthalpy of this substance. Alright, so actually we just proved the Gibbs-Helmholtz equation. If you look at one as a baric process, the first derivative of G over T with respect to T is negative H over T squared. And then if you look at the first derivative of G over T versus 1 over T, the derivative is H. Again, if you plot a graph of G over T versus T, the slope is negative H over T squared. If you make a graph of G over T versus 1 over T, the slope is H. At a constant pressure, again, we have this Gibbs-Helmholtz equation. One is here, one is here. Okay, if we know for sure the pressure is constant, we can write this two equation in the form of single variable equations. All right, so over here, just keep this in mind. Pressure is constant. And now at constant pressure, we can integrate both sides. We can move this exact differential of 1 over T to the right hand side, and then we integrate both sides. Well, if this H is roughly constant within this T1 to T2 interval, so again, if this H is approximately independent of temperature, we can take this H out of the integral. And then we have this equation. G over T at temperature 2 minus G over T at temperature 1 is equal to H times the difference between 1 over T2 and 1 over T1. So from here to here, we made one assumption that this H, this enthalpy, is approximately a constant between T1 and T2. This is not always true, but if you're looking at a reaction, then the CPM of the products cancels the CPM of the reactants mostly. Therefore, delta CPM is fairly small. So we can say, well, the enthalpy change of a reaction is roughly a constant given a moderate temperature range. So if we make that assumption and then we apply this equation to the product, we get one equation. We apply this to the reactants, we get another equation. We take the difference between the two equations, one for the product, one for the reactant. Remember, product minus reactant. That's the chemical reaction. Therefore, we have this equation here. Okay, going from here to here, what you need to do is to apply this equation to the products and then to the reactants. And then you get two equations, take the difference, you get this one. Okay, the Gibbs energy of reaction over T at temperature 2 minus delta G over T at temperature 1 is equal to the enthalpy of the reaction times 1 over T2 minus 1 over T1. Similarly, we can look at one specific reaction, one specific type of formation reaction, and then we get this equation for free. It comes from this equation. All right, so now let's look at this enthalpy of reaction and enthalpy of formation. Again, they do not change with temperature significantly only because the CPM of the products cancel the CPM of the reactants mostly. All right, so as long as T1 and T2 do not differ significantly, we have these two equations. They are very, very convenient for us to predict the Gibbs energy of reaction at a different temperature, given the Gibbs energy of reaction at one temperature. Usually, the room temperature data is given, and then we can determine the delta G of R at a different temperature. And also, if the Gibbs energy of formation is given at the room temperature, you just plug in the room temperature data here, and 298 K here, 298 K here. And then if you want to know what's the Gibbs energy of formation at 500 K, just plug in 500 K here. Also, you need to know the enthalpy of formation, of course. And plugging all the numbers, you will be able to get the Gibbs energy of formation at a different temperature.